In the first lecture, we will cover some important concepts in probability. Let us start from a sketch that tells us the concept of statistical inference. Here, a population is the entire group of interest. A sample is a small part of the population that we have the data and are ready to measure some statistic, which summarize some characteristics about the sample. The inference process let us use the sample statistic to make conclusions about the parameter that is associated with the population. So, we draw the sample from the population, study the sample to get the statistic, and use the statistic to estimate the parameter of the population as statistical inference. For example, we are interested in estimating the average height of male adults in the US. So, here the population is male adults in the US. Obviously, it is impossible to measure all male adult heights due to the extremely large population size. So, we may randomly select a sample from the population and get the sample mean. The average height of all male adults in the sample. The sample mean is a statistic. If the sample is truly random, then the sample mean would be an unbiased estimate of the population mean. The average height of all male adults in the US. Thus, we may use the sample mean as an estimate of the population mean, which is inference. As long as inference is involved, we need to report both the point estimate and the variability. Why the point estimate alone is not enough in inference? Because the sample mean depends on the sample. It may not be equal to the population mean. The sample mean is an estimate of the population mean. The variability tells us how accurate the estimate is. This is a very important concept in statistics. Statistics is about the probability. So let's begin from the event and its probability. First, the sample space. The sample space is the set of all possible outcomes of an experiment. The event is a subset of the sample space. For example, if we toss a coin, then we may have head or tail. Then the sample space is the set of head and tail. The event could be we get a head, for example. If events A and B have no outcomes in common, then they are disjoint. If event A is we get a head, and event B is we get a tail, then A and B are disjoint. Set is an important concept in mathematics, and here are the basics. Both the sample space and the event are sets. The common set operators include the intersection, the union, and the complement. For example, intersection of A and B means events A and B both occur. Union of A and B means A or B occurs. And the complement of A means A does not occur. So the intersection means and, the union means or, and complement means not. Here are some basic set laws such as commutative law, associative law, distributive law, and De Morgan's law. The probability is the chance or likelihood of events occurring in the sample space. Three axioms of the probabilities. First, the probability of the sample space is 1, since the sample space includes all outcomes. Second, the probability of an event is always non-negative. And third, the union of two events, A and B, is the sum of PA and PB if they are disjoint. From the three axioms, we may also have the following properties. This forms the concept of probability. After we learn the set basics and the properties of the probability, we may study the probability for multiple events. For simplicity, we focus on two events. We have the joint probability, the probability of two events happening at the same time. For example, we toss a coin twice, and the joint probability may be used to represent the two tossings. If we are interested in the probability of one event, irrespective of the outcome of the other event, then we have the marginal probability as PA or PB. So the marginal probability is just the probability of one event. Conditional probability is the probability of one event occurring, given that the other event occurs. For example, PA given B means the probability of event A occurring given event B occurs. And PB given A means the probability of event B occurring given event A occurs. The conditional probability PA given B is the joint probability PA and B divided by the marginal probability PB. Also, the probability of event B occurring given event A occurs is the joint probability PA and B divided by PA. If the occurrence of one event does not affect the probability of the other event, then the two events are independent. In the coin tossing example, let's say event A is the first toss is head, and event B is the second toss is head. So normally, the chance of the second event B does not affect the chance of the first event A. Thus, the two events are independent. When the two events are independent, then the marginal probability is equal to the conditional probability. Also, for independent events, the joint probability is the product of their marginal probabilities. The joint probability of both tossings are head is the probability of the first tossing is head multiply the probability of the second tossing is head. So the joint probability here is 25%. Now let's look at an example. Someone randomly chooses one hat from three hats with different colors, red, blue, and black. So what is the chance that it is a blue hat? 1/3, right? If we define event A as the picked hat is blue. Then we have PA is 1 over 3. And he put the hat on my brother's head. I saw it was indeed the blue hat. Then he picked another hat from the remaining 2 hats and put on my head. I couldn't see the hat on my head. What is the chance that I wear a red hat? If even the B is the hat on my head is red, then there is 50% chance that I wear the red hat, since I know my brother wears the blue hat. This probability is based on the fact that A is blue, and thus PB given A is 1 over 2. So what is the chance that I have a red hat and my brother has a blue hat? Using the formula, the joint probability PA and B is PA multiply PB given A, which is 1 over 6. If we don't realize the 2 picks are dependent, then we may have PA and B is 1 over 9, which is not correct. In the example, the 2 events A and B are dependent. If the 2 events are dependent, then the marginal probability is not equal to the conditional probability. Here, PB is the marginal probability of the second pick is a red hat, meaning the probability of picking the red hat without telling me any information about the first pick. Thus, in this case, the marginal probability PB is 1 over 3, and it is not equal to the conditional probability PB given A, which is 1 over 2. So, the 2 events are dependent. If we replace the blue hat after the first pick, and we have 3 hats to choose from in the second pick, then have a join with replacement. In this case, 2 picks are independent, and PA and B is 1 over 9. Thus, sampling with replacement leads to an independent sample. We may use the joint, marginal, and conditional probabilities to solve some interesting problems. Here we have one example. There is 30% chance of rain and 70% chance of no rain tomorrow. Also, there is 80% chance that you drive if it rains, and 80% chance you walk if it doesn't rain. The question is, if you drive, what is the chance of no rain? The easiest way to answer this kind of problem is through the contingency table, also known as a cross tabulation. First, we need to set rain as event A and drive as event B. Then we construct the frame of the table like this, and we write the joint probabilities in the green cells and the marginal probabilities in the gray cells. The marginal probability of event A is known and may be filled in here, as well as its complement. We don't know the marginal probability of event B yet, but with the help of the conditional probabilities, we may calculate the joint probabilities PA and B and PAC and BC through the formula. The joint probability PA and B is the marginal probability PA multiply the conditional probability PB given A, which is 24%. Similarly, we can calculate the joint probability of no rain and work, which is 56%. We fill in the table, and then the joint probability of rain and work is 30% minus 24%, so it is 6%. And the joint probability of no rain and drive is 14%. From the joint probabilities, we may calculate the marginal probabilities of event B. Thus, we complete the contingency table. The chance of no rain if you drive is the conditional probability PAC given B, which is PAC and B divided by PB, which is about 37%. Through the example, we may understand how to use a contingency table. In summary, we studied the statistical inference and the probability in this lecture. In the statistical inference, a sample is randomly drawn from a population, and certain statistics are measured from the sample. From the statistics, we may make inference to the parameters of the population. We need to report both the point estimate and the variability when we make inference. In probability, we learned the sample space is the set of all possible outcomes of the experiment, and the event is a subset of the sample space. The basic operations of the sets include intersection, union, and complement. The probability is the chance or likelihood of events occurring in the sample space. When we have more than one event, we have the joint probability, the marginal probability, and the conditional probability. The joint probability of events A and B is the probability of both events occurring. The marginal probability is the probability of one event alone, and the conditional probability is the probability of one event occurring given that the other event occurs. Their relationships are described by this formula. The joint probability is the conditional probability multiply the corresponding marginal probability. The two events are independent when knowledge of one event tells us nothing about the other event. Thus, for independent events, the conditional probability PA given B is equal to the marginal probability PA.